Okay, the topic of this video is going to be marine terraces on volcanic landmasses. This is a seamount not too far from Fiji, and we can see it's got some really nice, clear and distinct marine terraces that were made from the ocean currents, not ocean waves, but ocean currents that washed around them. Now, that's Fiji there. Let's go over and check out these islands up here. I think this is a good one here. So you can clearly see the steps, right? So when you study terraces, it's a cliff and terrace step sequence, just like riverbanks have a cliff and terrace step sequence. Now the altitude of this this top terrace here is 900 feet. So that's quite amazing to have something terraced up so high right next to the ocean on a volcanic landmass. Now, the thing about volcanic landmasses is they grow from overflowing lava, right? So this volcano would have lava, and then that's how it would overflow, and that's how you'd get the landmass growing. Now, it is possible that there'd also be tectonic forces at play. So it's not a complete fact that it's only from the overflowing lava. But nonetheless, when we look at these terraces, it looks as though the way the terraces are shaped close together and the way they're so distinct and clearly defined, it reminds us of something we'd find in the channeled scablands, where we find river terraces. The step sequences spaced out and clearly made. Now, if this was made from tectonic uplift, the uplift is so slow, it's, moving at the speed of a fingernail. That's not going to give enough speed to preserve the clear terraces. Okay? See how these terraces are nice and clear? That's indicating a rapid decrease in water level, just as the Columbia River experienced a rapid decrease in water level. Okay? So let's test the theory of, let's say this was from tectonic uplift, right? From a plate, it looks like we've got a trench here, so that's where two plates are colliding, and maybe that's what caused the uplift responsible for the marine terraces, and nothing really to do with ocean currents. It's more of ocean waves over the course of long time, right? Those are the two theories: catastrophic ocean currents or uplift and ocean waves over the long time. So how can we test this theory? Well, we can go to Africa, which is the north end of Africa is a subducting plate, meaning it subducts under the Eurasian plate. And this is what is responsible for the mountain ranges of southern Europe. Okay, so Greece, Italy, these mountain ranges are supposedly, this is what the scientists say, are formed from North Africa colliding and sliding underneath the Eurasian plate. So if that's the case, if the real understanding of marine terraces comes from tectonics, then there absolutely should not be marine terraces on the front end of a subducting plate. So let's test that theory, and let's look at Libya. This peninsula has one of the best marine terraces in the entire world. And let's check the elevation on this first one, 300 meters. And it goes up to 470 meters. And you can just keep, because this is sandstone, it's so well preserved, you can clearly see this marine terrace line, and then you see terraces on this land. So there's big terraces and there's small terraces, and they fit right in seamlessly with river terraces, which these ravines are actually quite substantial. They remind us of the Grand Canyon or some feature like it. I mean, there are Grand Canyon-like features all over the world, but that's a topic of another video. But let's go back up here and see these terraces. We can see how We get little mesas forming and incredibly intricate. Look at these terraces. These are very clearly river terraces, except for they're on the coast and they're up high in extreme elevation. This is 818 meters. I'm American, so we're going to have to figure out what that is in feet. Times 3.28, 2,680 feet in elevation. So when we go to our spot here, the elevation is only 900 feet. So there's a big difference. So when we're testing our theory of uplift, this being a place that's going to experience uplift, and this being a place that's supposedly subducting, and it's over 2,000 feet in elevation, full of marine terraces and river terraces, that's not exactly making that tectonic theory hold too much weight. Okay, now I'm going to let you guys in on the secret of terraces and the secret of marine terraces. It's from a sweeping ocean current. So we can follow this all the way around. And we can see that this is a big bay here. And we follow this in. This is a valley. And we see a lot of fluvial action on this landscape. We see parallel ruts, right? Wind can't carve rock into parallel ruts and do all this. So we know that because of the rutting found in rocks, when we then go back and we look at the sand, and we see that the wind doesn't move sand in such detailed patterns, we can then say, okay, well, these are fluvial features, and these are sediment lobes and drumlins and mounds and all sorts of other fluvial features and ripples. We find all sorts of amazing features, and they tell us current direction, and they actually show us an inland current direction that sweeps in, comes around megascale river, right? Come in. Let's find some megascale ripples. It's not hard to find them. Doesn't matter if you're in China or Nebraska or anywhere, you're going to find some megascale ripples. And then you can follow this ocean current and you can literally see exactly how it sweeps around and goes right back into the ocean. So that's the secret to marine terraces. Okay, so let's go to Japan and see if we can find some cool marine terraces. Now that we know a little secret about it. So here we find some nice cliff and terrace step sequences. 1, 2, 3. This being the nicest one, really. Very distinct. I mean, imagine you're standing on that bluff and you're thinking about how that used to be the ocean. Okay. And let's go maybe down to Okinawa. Find a cool little circular island with some cool little terraces on it. Right, so we can check these out. Now these terraces don't line up. They're supposedly in the same ocean. Well, not supposedly, they obviously are in the same ocean, but they don't got the right terraces. It's not because there's a difference in uplift, but a different in local ocean currents. Okay, now you're figuring it out. Let's check out this here. 1, 2, 3. Not bad. Let's see what I was pointing out on this one. Not sure what this is. Yeah, it's not a very good one, but it is flat. Let's go back. Let's go up to let's go to Russia. Guess this one must be sick. Let's check it out. This is the Bering Island. So we can see terrace number 1, Scablands. Terrace number 2, Scablands. Terrace number 3, and then ripples. How do you like that? I mean, you can't even make this stuff up. It's too obvious. I feel like, I mean, look at this. You're telling me those aren't ripples? I don't know what to tell you then. Yeah, so ripples on hillsides, that's actually a common feature. From California to Oregon to the Bering Islands, you can find them in uh, South America and Africa. So the wavelength on this is only 20 feet in wavelength. They're not massive, but very distinctly ripples. Kind of reminds me of a spot in Mexico. But yeah, man, that's sick. And then you kind of see, okay, well, if these are all ripples, are you talking about this being an accretion ridge? Maybe. Let's just keep going uphill. Let's see if we find anything else. Yeah, it's pretty nice. How far does it go? I mean, this right here's a terrace. Anyways, Bering Island is a great spot, full of nice evidence of ocean currents. Now, this is another good spot. See the way it curves around? That, to me, is a feature that helps me understand and helps prove that it's not just waves washing into shore. Waves washing into shore, that's not what made marine terraces. Okay, it's ocean currents sweeping around them. So when it comes around and it curves and you get the centripetal force of a river, and then that curve to it, and then it goes this way. Then you get another one coming around here and curving around. That's letting us know that ocean currents played a role. Okay, where am I at here? This is the Philippines. Or no, it's not the Philippines. The Philippines are over here. This is... Let's just see what we're talking about here. It's everything. Guam. We're over by Guam. See if Guam's got anything going on. Okay. Terraces, I see you. This right here is a nice terrace, though. I like this one because here you've got a nice cliff that only preserves one set of data. Right? One set of data is terrace here, cliff. But when you go just not too far, then you get a whole, you're accessing more data. Terrace, cliff, terrace, cliff, terrace, cliff, terrace, cliff, terrace, cliff, terrace. So more data is preserved in certain locations. And the elevation of this, 183 meters. Okay, not bad. Really flat terrace, right? So that's because a bottom of a river makes a terrace. The bottom of the ocean makes a terrace. You look at underwater features, a lot of underwater features are terraced. Let's check out this spot here. Yep, that's got really nice terraces on it. Formed quickly. Let's see if this is so this is what I was talking about. It's completely underwater and you get a really nice, perfectly flat terrace. It's from the ocean current. Okay. Let's go. Where should we go? Let's go to on this archipelago, but that goes between Alaska and Russia. Pick this little island. That's got a beautiful cataract formation in it and a ton of circular lakes, right? We know what those are, scours. Okay, not anything other than scours, but let's go in here. Oh, this is really cool. Bunch of lake shorelines. What does that remind us of? Maybe the Missoula Basin, right? The hills in Montana. Maybe it reminds you of Utah from the Bonneville flood. But this is an ocean current here, and the elevation is not too impressive. And then you get right up to the marine terrace. So you have marine terraces seamlessly fitting with ocean lakeshore lines, ocean accretion ridges, right? So it's the ocean current again. And you can see how they've got roundedness to them. Let's just keep going down here and seeing all the details. It's really well preserved, especially for a spot that should have been covered in glaciers, and ice sheets should have bulldozed all this. Let's take a peep at this. Yeah, that's pretty cool. But one thing that I think is really cool is these lakes here, right? So I'm saying this is all flat and terraced because an ocean current swept over it. Well, these lakes actually show us the direction of that ocean current. Okay, so you can see how this is triangular shaped. We can see this is a front edge here of a scarp edge, escarpment, circular lake, escarpment edge. Right here we can see a scarp edge that's showing a current that came through here, right? That's why we get these straight lines on it. But before that, the front edge was coming across this way. And then when we get a nice rounded oval shape, that's from the ocean current going back and forth. So the ocean current went back and forth, but primarily from the triangular shape of this, it's showing that it came down screen. And there we can know that there was an ocean current that swept this way. And it obviously probably went back and forth. Now when we go to... Oh, I'm getting ahead of myself. Where's this spot? Okay, yeah. So now we're in the Oregon salt scablands, and we get the same feature. Scarp edge, little, one shouldering right next to it. Scarp edge, tail. Right here you can see the tail. So these are directional features. This shows a directional feature. It comes across here. That's obviously the front. And then the tail is less organized. And then you got some nice rock, streamlined and terraced and all that. So, yeah, that's basically this right here. This spot in the Oregon scablands, bunch of parallel canyons and directional scours helps us understand this feature here. And also this feature here being a scarp edge, aka a shallow cataract, which looks just like this here, except for it's on a larger scale. So this is in the middle of a valley. Just as water dove down here and created this, so it also swept this way and created this nice big scarp edge. And then we can see accretion ridges along here as well. And that formed much later. Okay. And since we're on the topic of ocean currents sweeping across land, this is Madagascar. These are obviously ripples. 1,300 feet in wavelength. So obviously there was a big ocean current that swept along here and moved the sediment. Right, all this is pushed sediment lobes, right? You can see these features. And the directional features, so we know it went upstream. And then we're going to find that they start seamlessly fitting with marine terraces. Right here we get more ripples. Probably 1,000 feet in wavelength. And then now we're starting to seamlessly fit with this marine terrace, which then has smaller terraces in it. And then we get a little parallel salt scabland action. Accretion ridges, ripples, kind of right on, and then sediment lobes flowing upwards. Right, you see the way that these are all flowing upwards. So some people, they're kind of confusing features because if you look at it the other way, you can understand it. Oh, they were streamlined. But you have to understand that the sediment was there first as a ripple, okay? It was first laid out as a ripple, and then it got pushed forward. And you can see this happen live if you look at a river with a camera, and I've got videos of it. if you want to look at my fluid dynamics video. But yeah, really love the terraces in Madagascar. Look at this. So does that not look like the Grand Canyon or Washington or something? Of course. And then that is being correlated with marine canyons or marine terraces that have little directional scours on them. Okay, so I'm just going to go through the earth and show you what's correlated with what. And I'm going to repeat myself a lot, but it's still going to be fascinating because we got fluvial sediment lobes right next to marine terraces. You know, what's that indicating? You know, I don't even need to, fully explain everything. I'm just showing you the erosion and how to interpret the erosion. That's really my only job on this channel. So yeah, these sediment lobes are sick. And then look at this. So now we actually get a streamlined feature. This being a streamlined feature, and then these being pushed sediment lobes. So how can we know for sure? Well, there's a trick. This is the steep side. That's called the face. The face is always leeward, okay, downstream, down current. So this having its steep face leeward means this is a pushed sediment feature. The fluvial sediment lobes, this isn't a good example of one. Let me find a better one. Okay. Their steep face is also leeward, indicating both of these, even though they're, shaped opposite directions, the steep face of both of these is on the same side, and that indicates the direction is both the same, even though right, so this is streamlined, this is a sediment lobe pushed forward. Okay. Now, there's an oversimplification when it comes to ripples. I've heard scientists say that, only the steep face of a ripple is leeward. That's not true at all. I'll do a video on that. There's many cases where it's symmetrical and the steep face is actually on the whatever's opposite of leeward. And now check out this streamlined feature. And then the sediment lobes. Yep, that's pretty sick. These sediment lobes, and they're tucked right in next to this terrace. Oh, too perfect. And they're flowing over it. And then we get nice canyons with some terracing in it. Then, of course, we've got the spot of the spots. You know I love this spot. Corrugated ripples, cataracts, fluvial sediment lobes. So all this to indicate ocean currents in a catastrophic way. Now, that's at complete contradiction to the theory of, this plate was diving under this plate and all these terraces formed, at the speed a fingernail grows. Well, I just don't see how the erosion and the evidence of all of these terraces I've showed you, they're not showing anything at fingernail speed. Okay? This is not fingernail speed when it's creating corrugated ripple patterns a mile in wavelength, right next to cataract features. Okay, it's a sweeping ocean current that was more catastrophic than we can even visualize. And we go over to this marine terrace here. It's going to be accompanied by some sediment lobes, indicating a current direction downscreen. And then all of this is all mounds, right? Organized mound features, which, happen to be the most widespread geologic mystery in the entire world. See all these mounds here? these mounds stretch for thousands of miles. And the reason why they can't understand how mounds form is because they don't understand that the ocean current is the secret to understanding the erosion of the earth. Okay, and with that, I'm going to end the video. Thank you guys for watching. I really appreciate it. And I hope you guys can give this video a like. If you got any questions, please leave a comment and share this with your friends. And thank you very much and have a great day. Goodbye.